Alright, so on a rare occasion, guys, I've decided to go ahead and do the second part in one sitting. So, yeah, so we're going to look at graphing these by hand. So, we already know how to determine end behavior. We know how to find the y-intercept now. Now we just need to kind of review on finding the zeros. Remember, the zeros are where the function's going to cross or touch, depending on the multiplicity, the x-axis. Okay. Now we've got a lot of practice finding the zeros of functions, of quadratic functions. Okay, we just set the function equal to 0 and we try to solve it for x. And depending on the type of function, there's various ways we go about doing that. I do want to say, though, that in the real world, guys, most polynomials, they're not nice ones like we see in math courses. Okay, these polynomials that we see in math courses, these have just been made up to illustrate the concepts that we're studying. So that's why a lot of the zeros end up being nice numbers. Or to find the zeros, we can factor the polynomial and set the factors equal to 0. Most of the time in the real world, the polynomials that are used, that's not the case. And you have to utilize numerical methods, different ways of estimating what a 0 might actually be. So I just wanted to throw that out there. All right. Okay, so again, remember, to find the zeros, you set the polynomial equal to 0, and you solve it for x. Okay, now this can, if it's a quadratic, this can involve, if it is factorable, you can factor it, but if it's not, you have to use the quadratic formula. Furthermore, if the polynomial is already factored, most of the work is going to be done for us. All we have to do is set the factors equal to 0 and solve for x. Okay, and that's what we're going to actually see in this next example. Example 4 right here. It says, sketch the graph of the polynomial function by hand. Okay. All right, well, looking at this one is not written in standard form. Okay, it's actually in factored form, so it's been factored for us, which when it comes to finding the zeros makes our life a lot easier. However, when it comes to determining the end behavior, it's not explicit the degree of this polynomial, but we can still figure it out. Because think about this, if we were to expand this, or in other words, multiply these two binomials by themselves, from this one you're going to end up getting an x squared term. You'll get an x term and a constant, of course. And then in this one here, you would get another x squared term. And if you were to multiply those, you would have x squared times x squared, which is x to the 5th, times this last x would make this a 5th degree polynomial. Okay? So in other words, your leading term here is going to have an x to the 5th in it. Now you'll have, if you were to multiply all these together, you'd probably have an x to the 4th, an x to the 3rd, etc. We don't care about those for the end behavior. And then finally, guys, this negative would make that leading term a negative x to the 5th. Okay? And so if we know what the leading term is going to be now, then we can figure out the end behavior. Okay? Because well, let's see, where do I write this? The leading coefficient will be negative, okay? And then the degree of the polynomial is going to be 5, which is odd. Okay? So again, if it's negative and odd, the tails will be doing something different. The left tail will be going up and the right tail will be going down. Okay, so the end behavior, the left tail will be going up, the right tail will be going down. Now for the y-intercept. Okay. Well, it'll be the point 0, comma, and then to actually see what the value of that y coordinate is, we need to plug 0 into the function. But this function is actually g of x. So I'm going to try to be consistent here. Now, this one is, this one you can figure out what that y coordinate is going to be by inspection as well. Because if you plug 0, you'll end up with numbers in these parentheses. And so if you square those numbers, or non-zero numbers rather, so here you would end up with 2, and 2 squared is 4. Here you would end up with negative 3, and negative 3 squared is 9. So you have 9 times 4, which is 36. But eventually you're going to have to multiply by this x. So if we're plugging 0 into all these x's, it doesn't really matter what we get out of these two parentheses. Everything's going to get multiplied by 0 ultimately. And so consequently the y coordinate will be 0. Okay? So this particular polynomial is going to cross right at the origin at this point 0, 0. Okay? Alright, and then the last thing we need to work on is finding the zeros of this function. Well, again, fortunately for us, this function is already in factored form. So if I set each of those factors equal to 0, and I can do this, negative x, that would be my first factor. My second factor would be x minus 3. Okay. Now note, because this factor has an exponent of 2, that means it occurs twice. So whatever 0 is associated with this factor, it will have a multiplicity of 2. Okay? And similarly for this last factor. The last factor is x plus 2. And so whatever 0 I obtain from it, it will also have a multiplicity of 2. Okay? Alright, well, these can almost be solved by inspection. Now here, technically, you would have to divide both sides by negative 1. And you can do that if you want, but ultimately what's going to happen is you're going to get x is equal to 0. And then over here you're going to need to add 3 to both sides. And you're going to get x is equal to 3. And over here you're going to subtract 2. You're going to get x is equal to negative 2. Now, let's go ahead and put the multiplicities in. So this first one, this first 0, 0 itself, it only occurred once, or I only had one factor, so it'll have a multiplicity of 1. Okay? But these last two zeros, because their factors occurred twice, they have multiplicities of 2. Now, why is this important? Because this tells us whether the function crosses or touches at these values. So when the multiplicity is odd, I'll just remind you the function will cross. So the function is going to cross at 0. When the multiplicity is even, like with these last two zeros, the function will touch or is tangent to the x-axis. Okay? I just put touch. Alright, now to sketch this by hand, what you would do is literally plot these zeros, or x-intercepts. You're going to have, let me zoom in. Okay, you're going to have one right here at 0. This is also the y-intercept as well. You're going to have one at 3. You have another one at negative 2. Okay. Okay, so this 0 is not just serving as a 0, but also as an x, as a y-intercept rather. Excuse me. And then what you do is you look at your end behavior and kind of figure out the orientation. So the left end needs to be up, and the right end needs to be down. So I can kind of sketch that in here. Well, redo that. Kind of sketch that. Okay. And the right end down. And then we need to figure out what's going on around these zeros. Well, at -2, because multiplicity is even, the function's going to touch. So it's going to come down, touch, turn around, go back up. It's not actually going to cross there, see? Come back up. Now, we don't know exactly how high up it goes. For that, we would have to choose some values of x that are within this interval and see what those corresponding y coordinates are to tell us how high this function actually goes. So I'm just going to assume it stays rather low. Comes back down to this 0, which is 0, right here. And it has a multiplicity of 1, which is an odd number. So that tells me that my function will cross the x-axis. Okay, so it'll actually cross. And then to get back to this last 0, it's evidently going to have to turn around again. And again, I don't know how low it goes. For that, I would have to do some further investigation. But it comes back up to this last 0, whose multiplicity is even as well. So it touches and turns around at that last 0 and then meets up with that last piece. Okay. Now remember, we're just kind of doing this by hand. If I wanted a real detailed graph of this function, then I would need to plug in, I would need to probably look at the table or come up with a table manually to get some more points. But let's go ahead and graph this in Desmos real quick, or your graphing calculator. So y equals -x times, in parentheses, I think it was x plus 3, and that was squared. And then our other factor was, no, this was a -3. And then our other factor was x plus 2, and it was squared. And this is what it looks like. And that is similar to what we got. Now, one thing you will notice is that the function actually goes quite high here before it actually turns around and comes back to this 0. And then same thing down here. Like I said, we didn't know exactly how high the function would go. You can see it comes all the way up here, to a y value beyond 17. And then down here, it goes quite down here, quite a ways, all the way down here to about, I don't know, -41.5 before turning around. Okay. But what I did in my notes is just a rough sketch. Alright, now we're going to look at one more. Example 5. So this one says sketch the graph of the polynomial function by hand. Also, guys, if in your homework, if the graphs are multiple choice, you may be able to figure out which graph it is just simply by knowing the end behavior. You may not even have to worry about finding the y-intercept or the zeros and their respective multiplicities. Alright, well, this particular polynomial is in standard form, so it'll be easy for us to figure out what the leading term is. It's just going to be 10x cubed. Okay. So the leading coefficient is +10, so it's a positive number. And the degree of the function, it's a third degree polynomial, it's cubic, okay, which is odd. So it's positive and odd. So the ends, or the end behavior, okay, the left end will be going down and the right end will be going up. The y-intercept, 0, to find that y value, we plug 0 into the function, and because this function is written in standard form, all these variable terms will disappear, and we're just going to be left with 36. So this one crosses the y-axis way up there at 36. In fact, my little Cartesian coordinate system here is not going to be adequate to show that. And then lastly, the zeros. okay, which correspond to the x-intercepts. We'll put that in here. Now they're not technically the same, but remember they're related. Well, to find those, we need to take this function, set it equal to 0, and solve for x. Well, this function's not factored, so we're going to have to factor it ourselves. So that'll give us a little bit of practice, extra practice. Factor by grouping. That's the way you're going to have to do this one. Okay. And like the reason I know that, guys, is because it has exactly 4 terms, and these problems are made up. Okay, so it's constructed such that it's factorable by grouping. So I'll group up the first 2 terms. I'll put a plus sign. Remember, if that third term is negative, make sure that negative follows that number, or follows that coefficient. And then what we do is we factor out a greatest common factor from each of these groups. So for my first group, I can see a 2, and I can see they both have at least x squared. Okay, so I'll take out a 2x squared. And if I did that, if you factor 2 from 10, you're left with 5. And if you take 2 factors of x from x cubed, you're left with just 1x. And then in my second term here, I won't have any x's left, but I will have a negative 2. Remember, factoring out the greatest common factor is the opposite or inverse of distributing. So really what I'm doing is I'm dividing out this 2x squared from both of these terms. Now let's go to the last 2 here. These 2, they don't both have x in common. Okay? So there's a lot of numbers they have in common, but the largest one is going to be negative 18. You may be wondering, well, why negative? Well, because I want my signs to match up with what I already have in this first set of parentheses. Okay. So if you go back and divide both of these by negative 18, negative 90 divided by negative 18 is positive 5. You'll have that x left. And 36 divided by negative 18 is negative 2. And so now you can see that I have a 5x minus 2 common to both of these terms. So then that becomes my greatest common factor. And I just plug in my second set of parentheses what I have left over, which will be the 2x squared and the minus 18. Okay. So I factor this, and I end up with 2 factors. Okay, so now I'm going to set each of these factors equal to 0. I'm going to solve them for x. So this first one right here, I need to add 2 and divide by 5. So I get 5x is equal to 2. Divide both sides by 5. I get x is equal to 2/5. So that's one of my zeros. Now its multiplicity is 1 because this factor occurred only once. So the 0 associated with that factor just occurs once. And the same thing for this next one, guys. There's just one factor here, right? There's no exponent out here. So I may get more than one 0. I may get more than one value for x here, but each of those values will only have multiplicities of 1 because this factor is only occurring once. Okay. And in fact, that's what's going to happen. I can solve this directly for x. You could use the quadratic formula if you want because this is a quadratic equation. But I'm going to solve it directly for x because it's missing that middle term. If you remember from our study of those quadratic equations. Okay. And I'm going to divide both sides by 2. And I'll get that x squared is equal to 9. And here you'll take the square root of both sides. And remember, when you're doing this, you actually get two roots. You get a positive and a negative. So the square root of x squared is x, the square root of 9 is 3, so we get both a positive and a negative 3. So we end up with two distinct zeros, but they each just have multiplicities of 1. Furthermore, think about this, guys. This is a third-degree polynomial. So it cannot have more than 3 zeros. Well, the only way, since I came up with 3 distinct zeros, they must all have multiplicities of 1. Because if they have multiplicities greater than 1, then it would be as if this polynomial has more than 3 zeros. And that's impossible. Alright, so I'm going to do this one the way I did the last one. I'm going to start by plotting where my zeros are going to be at negative 3, positive 3, and then 2/5. Let me zoom in a little bit here. So negative 3, positive 3, and 2/5 is the same as 0.4, so it'll be about right there. And then I would plot my y-intercept. Well, that one's going to be off the screen, right, because it's way up there at 36. So what I'll do is just extend this y-axis, and we'll pretend that 36 is right there. Okay. So there's my y-intercept. And then we're going to look at the end behavior. The left side is down, the right side is up. So we'll kind of sketch this in. The right side is up. Now I'm going to kind of fill in based on the multiplicities of these zeros. Well, the multiplicities are all 1, and 1 is an odd number. So at each of these zeros, the function will cross the x-axis. Okay, so I'm going to cross right here. Now, before I can get to this next zero at 2/5, because it's on the right-hand side of the y-axis, I need to first come all the way up here to my y-intercept. Cross, and then I take a deep dive all the way down to this zero. I cross again, and again, I don't know how low this function goes. I'm just going to turn it around right here, go back up, and cross at that last zero. Okay, so we're kind of drawing a sketch of this graph or this function with limited information. But that would be enough information if this question were multiple choice. You could pick out the right graph. Okay. I will actually plug this one, or graph this one, in Desmos so that you can see. 10x cubed minus 4x squared. Get to it. Minus 4x squared minus 90x plus 36, if I'm not mistaken. Yeah, and we see that. We see the function crossing here at negative 3. It's crossing right here at 2/5. And it's crossing right here at 3. Again, you know, we didn't know how low this function goes before it turns around. Evidently, it's quite a ways. See that? So, but let's come up here and see if the function is crossing the y-axis at 36. And it's kind of hard to tell, but it is. Here's 36. The function, interestingly, the function goes way above 36, turns around, comes back down, and then crosses at 36 before coming all the way down here to this next zero. And that's actually something that I didn't capture in my graph. See, I didn't know it actually came way up here above, then came back down, crossed the y-axis, and then down here and crosses the x-axis. Okay. Alright, well that about concludes section 8.2. A lot of these you can just graph in your calculator, guys, but being able to figure or ascertain this information by hand is really important. To algebraically find those zeros, okay? And also to know how the multiplicity of the zero corresponds to whether the function is going to cross or simply touch the x-axis at that value of x. Alright, well, we'll continue our investigation in 8.3.